Hello and welcome everyone to my talk about Techvet, vetting malware tags using explainable machine learning. My name is Lukas Pirch and this is joint work with Alexander Warnecke, Christian Bresnegger and Konrad Rieck. Today I want to show you a brief overview about our work and share some interesting insights that we gained throughout our research. So the overall goal of Techvet is to provide reliable evidence for assessing the quality of malware tags. What does that mean? Consider the situation, which is quite common among large companies, that they have to face a lot of malware. Therefore, they build malware collections and try to analyze them. And to do so, they provide tags for each malware sample that they apply on them to be able to filter for these tags, or just have some sort of relevant piece of information that is associated with that malware. These could be, for example, malware families, which are commonly known from antivirus products, or behavior tags, or different kinds of things that are the result of the analysis that the analyst does. So what we asked is, how does that relate to the actual behavior of the malware? Currently, there is no good way to provide evidence for or an explanation for these tagging processes. And this is a problem. If you consider, for example, an antivirus product, which is most of them are proprietary and do not share their inner workings, you might ask, why is this certain family assigned to that sample? And to get an answer for that, we designed TagVet, which aims at providing explanations from a behavioral perspective. So let me show you how that works in a kind of overview. Our system is devised mainly of 3 steps. So we assume we already have the dataset collection and also some sort of tags, which we would like to explain now. What we did first is a dynamic analysis. We executed the malware samples in a sandbox environment. In our case, this has been the MRay analyzer sandbox. And this sandbox not only executes the malware, but it also monitors the function calls and its arguments in the Windows API. And it assigns automatically some sort of behavior tags. These are indicators for potentially malicious activities in the sandbox. And these also get assigned to the malware reports. We will use that as a certain type of tags later in our experiments. So what we take for our system is the behavior report, and each report is typically ranges from 1,000 function calls to several tens of thousand function calls, so it can be quite long. And we try to use machine learning to find the relevant spots in these reports. To do so, we train a so-called surrogate model. In the next step, which is called the tag prediction here, I will go into more detail about that in a second. And we try to train a neural network to predict the tag, which comes from a potentially unknown tagging procedure from the behavior report. And in the final step, we use explainable machine learning to and apply that on our white box model to be able to explain the decision of the neural network and thereby generate an explanation for the tag itself. First of all, we have, of course, to observe the behavior of malware, and this is partly a complicated step and also involves some filtering, some pre-processing, which I would like to talk about at first, because this is a really important step for the machine learning in the downstream process. So let's have a look at that. Here we see an example that has been generated by the MRay analyzer sandbox. And as you can see, this is a structured data format. It is XML, which contains a sequence of function calls. In this snippet that I show, we only see 2 function calls, but you already know that there are usually way more than that. And we see the arguments of the function call and some additional information in the XML attributes and their values. And the first thing we did to have really a linear data structure is to look at these nested XML tags, which describe objects in the operating system. In this case, a file object, for example. And as you can observe, these are referenced by identifiers, and we can resolve these identifiers and inline their attributes into the function calls to receive really a linear structure and a sequence of function calls, which have all the relevant information directly attached to that XML tag. Next, we see that there is some volatile information. For example, the timestamp or the memory offset of some binary data or the function call ID. This is information that is likely to change between multiple executions of the same malware. This would be just noise in terms of the machine learning and also for the analyst in the explanations, because this doesn't describe really the behavior of the malware, but more the details of the execution. We filter these out, and this already shortens the reports quite a bit. But we also see that, for example, in some of the values, there is more important information, and parts of that are maybe less important. Like in the file name, you see the randomly generated Sandbox username and a random file name for the executable that is being dropped by the malware. And we would like to replace that with a more generic string that indicates that this has been random. For that, we split each of the values at common delimiters. For file names, this is the / token in Windows and the dot character for file extensions. And we count each token occurrence in each per document, so once per document, and filter out rare tokens such that we can replace them with a placeholder token, in our case the start character, and reassemble these strings using the original delimiters. This leaves us with a very concise representation and some sort of template and a generic description of the behavior. This still captures the notion of dropping some executable in that certain directory, but removes the irrelevant information. Finally, we see that there is still some duplicate information, which we filter out in the final step, where we say, okay, the symbol name, the post symbol name are, for example, the same just after a normalization. The same goes for the file name, which is just a lowercase version of the mixed case file name original. And also there are some XML attributes that are constant in the whole dataset. For example, the symbol offset is always 0 in our case, which is why we also filter that out. This is the final representation that we use for the behavior reports, and which is the input for our subsequent machine learning tasks. So after all the hard work of pre-processing and cleaning up the data, we are able to apply machine learning on these behavior reports. The goal is to predict the tags from these reports, and in our experiments we used in total 3 different types of tags. The first type are family labels, which we collected from VirusShare. That is an online platform where we could collect several family labels from various antivirus products, which we then normalized to a single family label per malware sample using the tool AV class. The second type of malware tags is the sandbox tags that are attached to each sample after execution. So per sample, there may be 1 or more of these tags, depending on how many indicators have matched in this report. These are behavioral tags. And as a third kind of tags, we performed a clustering on the reports themselves. We embedded them into a vector space and applied a very default linkage clustering. And by measuring a certain metric, the silhouette score, we were able to identify how many clusters we would like to see. So we looked at the plot, which you can also see in our paper, and identified a peak in this plot. And at that point, we said, okay, this is the number of clusters we would like to have. In our case, this was 30. So we had 30 behavior clusters in which each cluster identifier corresponds to one tag in our case. These are the 3 types we would like to predict. And for that, we used a convolutional neural network, which I would like to explain to you next. What we see here is a representation of our behavior reports. We used a one-dimensional sequence. So we used the XML reports and put them into a sequence like the first function call with its arguments, followed by the second function call and its arguments, and so on. And the idea is to define a convolution that is able to not only capture the usage of function calls, but also the sequence. And this is especially useful because the reports are of variable length, and the convolutional neural network is able to handle that very efficiently. So to do so, we defined a convolutional filter whose size exactly matches the function call and the number of its arguments in the first convolutional layer. So this captures really the usage of a function together with its arguments. And since we have multiple of these filters, these can be learned in a different way, such that different usages can be represented in the neural network. In fact, we have to be able to define a fixed filter size. We have to pad all the function calls to a certain number of arguments. For that, we just analyzed the maximum number of arguments for any of the function calls and padded all function calls to that number, which you see in the bottom function call. We use this special pad token for that doesn't occur otherwise in the dataset. And this enables us to define this filter using this maximum number of arguments plus 1 for the function call itself, and to slide that over the input sequence in the way using a stride parameter that the first activation happens at the first function call, and then it jumps to the second function call, the third, and so on. This doesn't capture the sequence of function calls yet, but provides us with a series of activations that capture the function call usage. In a second convolutional layer, we feed the sequence of these activations into the convolution, and this is able to capture what we have already observed in the example that I've shown earlier in the behavior report, like creating a file and writing some binary data to that, or maybe previously downloading something using an HTTP request and writing that into the memory of a certain process, and in the meantime also creating a mutex or something. We are able to represent these kinds of sequences using the second convolutional layer. After that, we use a very standard approach of global max pooling layer and a fully connected layer to be able to predict the text from that. The maximum pooling reduces the dimensionality and compresses the activations to a fixed size. And at the end, we apply a softmax function, which transforms the final layer's activations to a probability vector, such that each entry of this vector resembles or corresponds to the probability that a certain tag is assigned to that piece of malware that is fed through the neural network. We train this neural network in a standard way, and the idea is then to apply then the explanation algorithm in the opposite direction in order to explain the decision of the neural network and thereby generate an explanation for the tag. For each of the 3 tag types, we trained a convolutional neural network using this architecture, and after we verified that these can indeed predict the tags from behavior reports, which they do with a high accuracy, we started generating explanations, which I would like to explain to you next. Regarding the explanation generation algorithm, we chose the layer-wise relevance propagation, which is a quite recent technique known from the domain of image processing, where they applied it to highlight the regions in images that are relevant to a certain classification. This has been successfully applied there, but it also applies to our domain, since we have a white box convolutional neural network model for which we know the model parameters, and also thereby also the gradient. And since this is a gradient-based technique, we can apply that here as well. And furthermore, it has a very, very nice property, which is called the conservation property, which basically says that the relevance scores for each layer sum up to the same values. And this ensures that the relevance scores from the output is transferred back to the input in a complete manner, and also produces concise explanations. This enables us to normalize the relevance scores between -1 and +1, where a positive score indicates that this particular feature speaks for the classification of a certain tag, and a negative score indicates that this feature speaks against the classification. So we see this has a really nice interpretability, and we use that to map back the relevance scores to the input features. And since we know their positions in the reports, it is very trivial to reconstruct the original string values of these features, regardless of the embedding step we did to embed them into a vector space. So if we have a look at this example for a sandbox tag, which says creating a process with a hidden window, we see that indeed for this tag it is very important to call the function process create. We see some blue shading on the ID0 proc create token, which indicates a medium relevance, but even more relevance on the create process function at ID2. And at position 4, we see the most relevant token, which is the create suspended parameter for the creation flags argument. As you can see, this is a very concise representation of how certain arguments are relevant. And also we have the context with a function call that belongs to that, because they are located near to each other. However, this layer-wise relevance propagation is a sample-based technique, so we receive an explanation for each of the samples. But when we would like to explain a whole tag, we need to aggregate multiple of these explanations. We do that by computing all the relevance scores for all samples and their features, and then we select just the top k most relevant features for that tag. In our case, we used k equals 10, so we selected the top 10 features, but this is a parameter that could be changed. And now we receive the most relevant tokens, and since we have knowledge about the XML structure of the reports, we can leverage that to reconstruct the context. So in this case, we would see that the create suspended token is the most relevant one, and we can infer from its position that the token before that is the argument name, and the token at the first position in that block is the function call, such that we don't only have a single token, which could be meaningless, but also the context of the function call and which argument it belongs to. Let me show you how that looks in practice. We did some qualitative experiments, which you can also read in our paper. But here I want to just show some quick example how that could look like. For example, for a different sandbox tag, attempting to connect to an unavailable TCP server, we immediately see that the socket connection function is here important. In the Windows API, this function is called connect, and it's combined with the parameter success equals false. So the socket connect function, which does not succeed corresponds to the textual description of the sandbox tag. Keep in mind that we did not give the neural network any hint on how to combine these function calls or tokens. We just collect the most relevant ones and reconstructed their context in the XML report. And as you can see, this leaves us with very concise and meaningful explanations for sandbox tags. We also did that for different kinds of tags, for example, for behavior clusters. And as you can see here, again, there are several instances of arguments for the same function call, where we would suspect that in that behavior cluster, this combination of arguments in that function call is very characteristic for malware in that behavior cluster. Here we see the modmap function, which maps a view of memory into another process. And apparently what is typical in that cluster is to create an empty view with a commit size equals 0, with execute read-write permissions on the memory page, and to load the memset function from the Windows API into the process memory of the malware. What you can do now is take this analysis, which is already useful in itself, but also take that to the next level by relating it to the distribution of family tags, for example, or other types of tags. In this case, I did that for families, and I observed that in that behavioral cluster are mainly ursnif and GOSI samples. And also, in the second chart, you see the distribution of ursnif and GOSI samples across all behavioral clusters. So this is the other way around. And we see that all of these samples indeed fall into that behavioral cluster. So this explanation, what we get is an evidence or a characteristic behavior of these two families that distinguishes them from all other families in the dataset. And this indicates, this combination of the distribution analysis and the explanation indicates that these two families are related from a behavioral perspective. Indeed they are. As far as I know, GOSI is a very old banking Trojan, and in 2010 its source code has been leaked and has been reused by the ursnif family later on. So this is a relation that we typically cannot observe in the behavior reports, but using the same source code implies the same behavior to some extent. And our Techvet system was able to find a unique behavior that really characterizes these two families and distinguishes that as the same for these two families, but distinguishes them from others. You can extend these kind of analysis to your use cases, and also, for example, could analyze one family explanation and look at how this is distributed across multiple behavior clusters to find several subgroups of a malware family or variants. And yeah, you can extend that to your needs. To quickly summarize what we have learned from our research during the Techvet paper is that we can actually provide concise and meaningful explanations, and that these help to build trust in external information sources for which we do not know the tagging process, for example. Also, as I've already previously talked about, we can see inconsistencies or consistencies between different approaches, and now have some sort of giving evidence about that and justify our decisions when saying, for example, that ursnif and GOSI are in fact the same malware. Keep in mind that there is also an inherent limitation, because in this experiment we just looked at the behavior of malware. We are actually not able to capture, for example, tagging that is derived from metadata, like the threat actor or the time span at which the malware has been active. So if you would like to apply that to your malware collection, keep in mind that you would need to reflect this in the features that you use. That's it for this talk. I would like to thank you now for tuning in and staying with me during this talk, and I'm happy to take your questions now in the Q&A. Thanks.